Hello everyone. In this session, we are going to study the work, kinetic energy, and potential energies. First topic is the work. And second topic is the kinetic energies. And the third topic is the potential energies. In our daily life, we often use the term work. In physics, the term work is important. We will define work with the formulas. The constant force of F is applied to a box, and the box is moving to the right with the displacement of the S. The definition of work is a product of the force magnitude of F and the displacement magnitude of S. So W work is equal to, so this is the work. Work is expressed F times S. The unit of work is a unit of force. This is a unit of force, newtons. And the unit of displacement, meters. So we introduce the unit of work is a joule. Joule is equal to the newton times meters. The direction of force is not parallel to the displacement sometimes. Then we use a vector. Applied force has an angle with respect to the displacement. So displacement vector is a displacement vectors. And the applied force is not parallel to the displacement vectors. Then we'd like to define the work. Only the parallel component is effect to the moving a box. So to be consistent with the work, force actually is a parallel component times the displacement. So among this force, actually we can decompose into the two directions. Parallel component of the F parallel and the perpendicular component F sub perpendiculars. And the F parallel is just important quantity to describe a work. So work can be expressed F parallel times S, magnitude of the displacement vectors. So to describe this quantity F parallel, if you consider this triangle, F parallel is equal to F cosine theta. So you can express F cosine theta is equal to the F parallel times displacement vectors. Then if you remember the definition of the scalar product, you can express this quantity using the scalar product. This is scalar product. F dot S. Then we have a positive work and negative work and zero work. In the case of the theta is between the 0 to the 90 degrees, the work becomes positive. When the applied force is this direction, for example, F, and displacement vector is this one, then theta is larger than the 90 degrees. In these situations, work becomes negative quantities. This is negative work. So even the negative work is defined. In our daily life, we don't use a negative work. We assume that the work is always positive. But in physics, we define the negative work. And also zero work, when the applied force is perpendicular with respect to the displacement vectors. In this situation, work is zero. If you take a small change of the displacement, then force is a constant. Force times the displacement. So this is the amount of work. The force times the displacement vectors, displacement of delta x. We can find the work done by applied force. Also, by changing the positions, we could obtain applied work, applied work, applied work, applied work. So this is actually the work is correspond to the areas under the curve. So area under the curves can be calculated using the integrals. So this is even if the force is changing with the positions. If we perform the integration calculations, we could find the work done on the object. And define the work with a constant force. Then force is constant. The areas under the curves correspond to the work. So in this situation, it's quite easy to calculate. Integral is equal to f times, this is x sub 2 minus x sub 1. This is f. The area can be calculated. F times x sub 2 minus x sub 1. This is correspond to displacement vector s, fs. When we want to calculate the work to stretch a spring, so to stretch the springs, we have to apply this amount of the force of the kx, because the spring is try to return to the original positions with the minus kx. So same amount of the force is applied to stretch a spring, the kx, and then positive directions. So opposite direction with respect to the force by a spring. The work you can calculate by performing the integral. So in this case, is f is a kx. The integral. This becomes 1 over 2 kx squares. And x is changing x sub 1 to the x sub 2. Then we have this. Is the amount of work to stretch a spring. Sometimes an object is moving on a curved path. Also, we'd like to define the work done on a curved path. The direction of the force is changing. Also, the displacement vector is changing with the positions. Then we have to take a small change of the dr on the curved path and apply the force. And take a scalar product with the f dot dr. This is the amount of work done on the object by the applied force. And then we have to sum up these small amount of work to find out the total amount of work is changing from the position of the r sub 1 to the r sub 2. So we sum up these dw's on the curved path. So this is the total amount of work done on the curved path. Okay, this is the end of this session.